Okay, well, I'm going to go ahead and get things started here with a few announcements. First of all, I want to thank you all for joining us here tonight. My name's Pete Eberle, and I'm with the Northern Chapter of the Colorado Renewable Energy Society, or CRES. For those of you who are new to our events, CRES and its local chapters provide education, policy advocacy, and community engagement that accelerate Colorado towards a carbon neutral future powered by 100% renewable energy. Founded in 1996, CRES is a statewide, nonpartisan 501c3 not-for-profit that's supported by our sustaining individual members and business members, as well as donations. Please visit www.cres-energy.org, that's CRES-energy.org, to learn more about the organization, become a member, or make a donation. Sign up for our newsletter and find our social media links, including our YouTube channel, which has over 100 recorded presentations going back several years. I do want to give special thanks to our Northern Colorado business members, Solaris Energy, Poudre Valley Rural Electric Association, Sandbox Solar, and Platte River Power Authority. So without further ado, I will go ahead and hand it off to Scott, and who is a professor of atmospheric science at Colorado State University.
Well, hello, thanks a lot, Pete. I'm going to talk about carbon capture methods this evening, and in particular was asked to sort of give a consideration of a bunch of different methods and strengths and weaknesses and so forth. So I have this fun little cartoon on the front page here. These two guys busy mopping the floor, but they're so busy mopping the floor they forgot to turn off the faucet. So that's kind of a nice analogy to what we're talking about here. I want to start with the Keeling curve. So Dave Keeling, back in the 50s, developed an instrument to measure CO2. Started measuring continuously at the top of a big volcano in Hawaii the year I was born, kind of incredible. And by the 1960s, Keeling and his colleagues had discovered that indeed the CO2 was going up, not dissolving just as quickly into the oceans as we were producing it with combustion, as had previously been hoped. But he was also able to show that the increase of CO2 in the atmosphere is only half of the rate at which we are producing CO2 by burning coal, oil, and gas. So pretty easy to count up all the emissions, even back in 1960s. And the conclusion was that half of the fossil CO2 was missing. It had gone missing. So then an incredible bad idea was hatched by the US and the Soviet Union. They used to test nuclear weapons in the atmosphere. And back in 1963, they signed a test ban treaty that they promised not to do that anymore. No more nuclear weapons tests in the atmosphere. So what do you think they did before it went into effect in 1964? Of course, bang, 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 bang. They tested dozens of bombs in the atmosphere, produced a huge spike of radioactive CO2, radiocarbon, which biologically and chemically behaves just like any other CO2, but because of the radioactivity, it's like it had a little sticker on its forehead that said, I was made in 1964. And then over the next 10 or 20 years, oceanographers went out and found the bomb radiocarbon in the oceans and were able to measure the rate at which CO2 dissolves into the oceans and is sequestered in the deep ocean. So we had a really good geochemical experiment. Unfortunately, it involved lots and lots of nuclear weapons testing in the atmosphere. Anyway, we have these commercial records that tell us how much fossil fuel is burned. The atmospheric increase can be directly measured just by sampling the air. The air is reasonably well mixed. It takes about a year for the air to completely mix around the world. And the CO2 is therefore sort of rising at the same rate everywhere on Earth. Then we subtract the ocean uptake, which is about half turns out the ocean uptake could only account for about half of the missing carbon. So we got 100% from fossil fuel, we got 50% from that's going into the atmosphere. The oceans are only taking up 25% of that fossil fuel as constrained by the bomb radiocarbon. injection into the oceans, and that left a missing sink of about 25% of fossil fuel. And this was basically known by, let's say 1975. So what the heck is happening to the other 25%? It pretty much has to be going into the land because, where else is there? There's the air, there's the ocean, and there's the land. So oceanographers back in the 1960s and 70s pretty much just hypothesized that since plants eat CO2 for a living, which we call photosynthesis, adding CO2 to the air is making them fatter, right? Making them bulk up. It's like the Girl Scout cookies theory of dieting. If there are Girl Scout cookies in my closet or my cabinet in the kitchen, my biomass increases over time. So the hypothesis was that since there's more plant food in the atmosphere, the plants must be get bigger, and that's where the extra 25% of fossil fuel emissions was going. In fact, you can do these experiments in greenhouses and show that, in fact, adding CO2 to the air in a greenhouse makes the plants grow bigger. These are rice plants grown in pots in a greenhouse, and I see at 30 parts per million, the plants are pathetic and they're dying. But by the time you get up to 800 parts per million, oh my God, they're growing like a jungle out there. However, this was an easy experiment to do, but it doesn't really explain where the carbon has gone, because it turns out that things die, right? It isn't just enough to grow plants, because plants die. And eventually all of the CO2 that goes into plants is then eaten. The carbon is eaten by bacteria and fungus and whatever, which respire that CO2 right back into the atmosphere. So the net life cycle carbon storage of any plant is zero. So we have kind of a conundrum here. We're missing 25% of the fossil fuel, but we can't really explain it just by increases in photosynthesis. It turns out that in fact, it is true that there is a carbon sink over land, and we now understand this much better than we did back in, say, 1975. But when we say that, what we are really claiming is that over many decades, plants are growing faster than they're dying. This is an amazing statement, and it's true. It's not true everywhere. It's not necessarily true in your backyard or in the Amazon, but it is true of the Earth as a whole. Since we started getting good measurements back in the 1950s, there has been an excess of growth of plants, or growth of biology minus decay of plants, and that has offset about 25% of fossil fuel combustion for decades, for my entire lifetime. So what about tropical deforestation? And what about cutting down the trees for subdivisions and Walmarts? What about plowing the prairies for crops? How is it possible that these plants are worldwide growing faster than they're dying? Part of it is nitrogen fertilization. We normally have nitrogen. Of course, the air is full of nitrogen. 80% of the air is nitrogen, but it is inert, chemically inert, biologically inert nitrogen in the air. The N2 is triply bound. You can't get N atoms out of air in order to make amino acids and proteins. It used to be that lightning and bacteria were the only sources of bioavailable nitrogen in the atmosphere. But in the early 20th century, German scientists Haber and Bosch invented manufactured fixed nitrogen, so chemical fertilizers. And that, of course, led to the Green Revolution and feeding billions of people. There's also combustion, which burns some air. You get N2 plus O2 to NO and NO2, and that stuff floats downwind and turns into fertilizer. It's like miracle grow from the skies. So not only are we giving the plants extra carbon, we're also giving them extra nitrogen. There's also changing land use. So we think of land use as a source of CO2 to the atmosphere with deforestation. But when I was a kid growing up in New England, we would find these lovely stone walls out in the woods, and I'd wonder what the heck was somebody doing, going to all the trouble to stack up all those rocks and build a stone wall out in the forest. Well, of course, it didn't used to be a forest, right? All of the land in New England was farms back in the 19th century. and actually across almost everything east of the Mississippi have been deforested to allow for family farms. But family farms went belly up in the 20th century. Everybody moved into town, got jobs in, you know, shoe factories and 7-Elevens and Walmarts, and allowed those woodlands and forests to regrow in the second half of the 20th century and into the 21st. So every molecule of wood in Vermont was derived from a CO2 molecule, actually many CO2 molecules. And there's a lot of the developed world that has been reforested as the sort of post-agrarian land use pattern has taken hold. Last thing I want to talk about with respect to the land is the Arctic. It's warming very, very fast up there, 3 times as fast as the rest of the world. And satellite data show that it is also greening. We have much of the Arctic with 50% longer growing seasons, frost-free seasons, than we had 50 years ago. That has allowed shrubs to invade into the tundra, forests to invade into the taiga, and there's overall a sort of invasion of woody plants up into what was formerly very low carbon landscapes, and that is sequestering a lot of carbon. So all of these different mechanisms are putting carbon into the land. The oceans also take up CO2. Fundamentally, it's the same chemistry as soda pop or beer. CO2 dissolves into water to make carbonic acid. That's why beer goes good with pizza. That's why Chardonnay goes well with brie. That's why I drink Pellegrino with my cheesy dinner. The CO2 dissolves twice as well in cold water as it does in warm water, which is why beer and soda go flat when you leave them on the kitchen table. But it's also the explanation for why the cold polar ocean soaks up CO2, carbonates the ocean, literally carbonation. Carbonic acid is acidifying the oceans, and it is then transported through the body of the ocean into the tropics, where the warm water then releases it through going flat. It turns out that the ocean, however, is not well mixed. The atmosphere is well mixed, but the ocean is not. The ocean is 13,000 feet deep, incredibly deep, and only the top couple of 100 meters of it is warm, tolerably warm. There's like a raft of warm water floating on the deep ocean, and that raft of water is exchanging chemistry with the atmosphere. But the big, deep Davy Jones locker bottom, not even just the bottom, but the entire body, but 95% of the mass of the ocean is cold, and it sits at the bottom, very, very thermally stable, hard to mix, takes 1,000 years for that stuff to turn over. The deep ocean is cold and inky black and doesn't know we're here yet. If you went and sampled the deep ocean, you find that the chemistry of the deep ocean is in equilibrium with air from 1,000 years ago. We know because we looked. We actually went out and sampled the entire freaking ocean with ships, with underpaid graduate students who are woken up every 30 miles and told to come out on deck, and they drop these tanks to the bottom of the ocean, and they sample all the different depths and bring it back to laboratories. This looks like lines on this map. Each of those lines is composed of dots, and at each one of those dots, those underpaid technicians dropped the flasks to the bottom of the ocean and came up with all this chemistry. And what we find is that the CO2, which is shown in red here, is only at the top of the ocean. The dissolved fossil fuel CO2 is confined to the top, few hundred feet of the ocean, and it takes a really long time to get down into the water. It's going to take thousands of years for the atmospheric fossil fuel CO2 to equilibrate chemically with the deep ocean. So we are doing sort of a planetary titration experiment. It's like the acid-base chemistry you did in high school. We are dripping some carbonic acid into that great big beaker, which is called the world ocean, and it is changing the chemistry of the ocean. But the ocean is really freaking big, and it's going to take a very, very long time for that titration experiment to go to completion. So where has all the carbon gone? It turns out that the oceans have taken up about half of the fossil fuel CO2 through solubility and also biology. The dead algae and so forth can sink down. Most of them decay in the surface, but some of them sink to the deep ocean and deliver that carbon to depth. That's called the biological pump. And on land, yes, plants eat CO2, so we give them extra CO2. At the same time, we give them extra nitrogen through fertilizer and through combustion. Land use change, primarily forest regrowth, suppressing forest fires, think Smokey the Bear, woody encroachment, and all that, as well as boreal warming, all contributing to a roughly 50% overall uptake of CO2 by the Earth system in the ocean and the land relative to the fossil fuels. Now, the sinks, the ocean sink and the land sink, will eventually fill up. They will saturate chemically, biologically, as nutrients are depleted and so forth. So the land in particular is very vulnerable to carbon loss. Only CO2 fertilization really has legs because, for example, once you've regrown those forests in New England, they're already regrown and they're no longer growing faster than they're dying. That sink goes away. You give your lawn a bunch of fertilizer and it'll grow faster, but if you give it 10 times more fertilizer, it doesn't grow 10 times faster. In fact, you'll probably burn it and then you don't have any more carbon uptake. The boreal warming may actually even be the worst one because a little bit of warming and you get shrubs in the tundra, but a lot of warming and you get thawing permafrost, and there's a tremendous amount of carbon in the permafrost that can then come out and bite you. So these sinks are kind of vulnerable. The ocean sink in the short term is quite safe and slow because the physical mixing against buoyancy is so slow, but eventually as the surface water warms, that mixing will slow and it will take a long time for the chemistry to equilibrate. One of the big things that I think you need to know about this problem is that the emissions will end. So I don't know if you guys can see my cursor, probably not, but the CO2 emissions certainly will end. These are 4 different emission scenarios going all the way out to the year 3000. Emissions are done by the 22nd century, no matter which scenarios you use, but the CO2 lasts much longer. The CO2 in the air is retained. Under those high emission scenarios, we have 1500 ppm in the atmosphere in 3000 AD, and that will stay in the air for many millennia, hundreds of thousands of years. The CO2 will take to dissipate from the atmosphere as it is used up. It's like we have a thermostat that only turns one way. There's like a ratchet in there. You can crank it up, but it will never be able to turn it back down. It's really kind of a big long-term problem to get rid of it. Now, in the even longer term, the geologic timescales, CO2 comes out of volcanoes and it is taken up by dissolving rocks. Okay, this is plate tectonics. You have the mid-ocean spreading ridges. The CO2 comes out into the atmosphere. But the CO2 is then consumed through the dissolving of minerals in mountains on land. And over geologic time, the seafloor spreading is basically balanced by uplift of rocks that then get weathered back down. And that turns into a thermostat, a negative feedback over millions and millions of years, where extra CO2 leads to warming, that leads to more erosion and more dissolving of the rocks, that leads to cooling, and vice versa. So eventually, long after we're gone, geology takes over, and some of the carbon sequestration things that I'm about to talk about have to do with trying to accelerate that geologic process of chemical weathering, rock weathering. Ultimately, though, the initial ocean invasion of the atmospheric CO2 from fossil fuels will take some millennia, some thousands of years, perhaps by 5000 AD. That ocean invasion of fossil fuel will be complete, at which time the carbonic acid has to react with seashells or other things made of calcium carbonate like coral reefs. That's very bad in the long run for marine biodiversity, but that will go on for hundreds of centuries. And then ultimately there'll be some perturbation, perhaps 10% of the fossil fuel, which has to actually react with igneous rocks over hundreds of thousands of years. That's the sort of geologic timescale. So this is where it's got to go. This ultimately means we have to stop setting stuff on fire, right? There's no way around this because the consequences are severe and the consequences last for many thousands of years. Not just you and me, but everybody everywhere forever will need to stop burning carbon for energy as soon as we possibly can. Now, I had a little video to show here from NOVA, but I can't show it because of limitations of GoToWebinar. Let me just say to you that when we talk about fossil fuel combustion, we are talking about an enormous amount of carbon. The amount of carbon that humans burn every year would fill the National Mall from the Capitol to the Washington Monument, all the way up to the top, sorry, the Capitol to the Lincoln Memorial, all the way to the top of the Washington Monument times 10, and we burn 10 times that much. So 10 gigatons, 10 billion tons of carbon a year are burned, and that turns into 37 gigatons of CO2, because the CO2 has oxygen and it weighs more than the carbon. So it's an unbelievable volume of carbon that we are adding to the atmosphere. And when we talk about carbon dioxide removal and cleaning up the mess, what we're talking about is removing masses that are of that scale. So tens of billions of tons of CO2 per year. And it's, of course, been many, many, many years worth of CO2 that we've already had. So really the question with cleaning up the mess comes down to whether we do it fast enough, whether we cut our emissions fast enough. So here is our overall greenhouse gas emissions. The CO2 is 37 gigatons a year. There's other greenhouse gases, methane, N2O, and so forth, that take us up close to 50. If we want to keep the global climate from warming more than 2 degrees Celsius above pre-industrial conditions, we have to follow that red line down to net zero emissions, certainly half of today's emissions very quickly, and then net zero emissions by the end of the century. The scenarios that have been modeled, for example, in IPCC, get there by making net zero emissions through having big negative emissions. So the blue area below the zero line here is negative greenhouse gas emissions. That is carbon removal technologies, and that is intended to offset some of this brown area above zero, which are emitting technologies, or for example, farming, agriculture, other kinds of land use change that produce CO2. So in order to reach net zero and keep climate from warming too much, many modeling scenarios are using negative CO2 emissions. And basically, the assumption is that we will not cut our positive emissions fast enough to hit net zero in time. And so we're going to need to go beyond these conventional abatement technologies and start relying on carbon removal technologies. So that's what I'm here to talk about. Here's a bunch of possible technologies that are out there. In particular, I'm going to talk about afforestation, which is this one on the right, reforestation, improved forest management. That is basically leveraging the natural carbon cycle, the fact that trees can be made to grow, or vegetation can be made to grow faster than it decays. We have seen that the natural carbon cycle is already achieving about a 50% emissions reduction in ways like that. So through intentional forest management, trying to increase the total carbon stored on land. There's also soil carbon sequestration through better farming practices. Probably the one that has been talked about the most is this one in the middle, which is biomass energy with carbon capture and storage. It's often called BECCS. That's BE for biomass energy, with CCS for carbon capture and storage. The idea is that we would grow, biomass energy crops like switchgrass or soy for diesel. Then we would transport those crops to places where we would extract the energy. Think of it as a big power plant. But then we would put scrubbers in the smokestacks and take the CO2 out. And keep it from going into the atmosphere. The third one that I will talk about at some length is direct air capture, where you run plain air, thin air, through chemicals, filters basically, that react the CO2 with a strong base, and then you collect the CO2 off of the strong base and get rid of it. All of those methods that I just talked about involve trying to store it for the long run, either in holes in the rocks, geologic formations, or by reacting it with special kinds of rocks that are highly reactive with CO2, like basalt, the black lava rock, or even better, peridotite, which is a green rock that comes from the Earth's mantle. Not very much of that available. But anyhow, if you can get some CO2 and stick it down in those rocks, you can form it into calcium carbonate, which is a long-term stable mineral. There is some work on the left-hand side of this diagram on accelerated chemical weathering. That basically means doing something to the rock, pulverizing the rock, feeding it with high concentration CO2 to make the CO2 go away. Or really, it's the same sort of thing in the ocean, changing the chemistry of the ocean in such a way that those kinds of calcium carbonate formation reactions happen in the ocean. So this is sort of a big suite of these negative CO2 emissions, sometimes called CDR, for carbon dioxide reduction. Let's start with the easiest one, and that is afforestation. So remember that all trees die, right? So it's not good enough to just have trees. Trees by themselves don't, on the net, take up any CO2, because all of the CO2 that they turn into trees during the course of their lifetime turns back into CO2 after they die. What you have to do to get a sink out of land management, forest management, is to replace non-forested land, that is low carbon land, with mature forest, that is high carbon land. So it doesn't have to be non-forest to forest, but it has to be from a land use type that has few kilograms of carbon per acre, and you replace that with a land use type that has lots of carbon per acre forever, right? That's the tough part, is that you can't go back on it. You can't like grow a forest and then cut it down for pulp and paper or 2x4s, because now it's no longer a high carbon landscape. You have to go from a low carbon landscape into a high carbon landscape permanently. The challenge here is basically land, right? We don't have enough land to do this. Most of the land that can support forests is already forested, right? Where could you grow forests? Well, Siberia, right? The Amazon. Where can't you grow forests? Well, Greenland, the Pacific, the Sahara. Those places can never have forests. So the land that can support forests basically already is forested. And then there's the land that could support forest but isn't currently forested. And normally what we call that is farms, right? Farms are the places that used to have trees and now we use them to grow food, or cities. So really, when we talk about afforestation as a carbon sink, what we're talking about is converting farms and cities into forests. And as you know, that's very expensive. I mean, how much does it cost to buy up prime farmland in Iowa or, you know, Manhattan real estate and put it permanently into forests? A somewhat harder sell, a harder thing to do is the one that IPCC is relying on the most in the econometric models that are used to assess these things. And that's called biomass energy with carbon capture and sequestration, BE with CCS or BECCS. So the idea here is that we replace the fossil fuel, offset the fossil fuel with biomass energy crops like switchgrass for ethanol or soy for biodiesel. We capture the concentrated CO2 from the power plant effluent and then store that liquefied CO2 forever, right? We have to concentrate the CO2 from the smokestacks. We have to make some sort of liquefied waste product. We have to pipe it or truck it or train it or ship it to some permanent repository where we pump it down into the ground and either store it in pore space in rocks, or we store it by reacting it with reactive minerals like basalt or peridotite. And the challenge here is, again, land, but now it's basically diverting land from food production to biomass energy crops, right? Instead of growing wheat, we would have to grow huge amounts of soy biodiesel or switchgrass ethanol, and that land would be taken out of food production. So, you know, this could be done. It is being done at some scale, but it's certainly not being done at the kind of scale that matches 37 billion tons of CO2 a year. And it would cost between $50 and $200 a ton of CO2 sequestered in this way. So this is starting to sound like a lot of money. Probably the hardest of these methods, the most difficult thing that we could possibly do, is to try to capture CO2 from ambient air. So this is a technology called direct air capture with carbon sequestration, either DAC or DAC-CS. This is where you blow ambient air with big fans over some sort of solvent or sorbent medium. So typically they are tiny glass or plastic beads that are coated with ammonia or amine solution that is high pH, and the CO2 from the air dissolves very readily in that high pH liquid or gel coating on these beads. And then once you've saturated the beads, you have to get the CO2 off of it. And this is actually where the energy is used, is typically use heat to extract the CO2 from that, that solution that you coated the beads with. And then you still have to store that liquefied CO2 forever, just like you do with BECCS or some of these other methods. The challenge is that it takes a huge amount of energy to gather dilute CO2 from thin air. It's essentially the opposite of taking concentrated carbon in a lump of coal and liberating it, right? Releasing it to be diluted in the world atmosphere. Now we actually have to gather it up molecule by molecule and extract it. And actually the energy is dominated by regenerating the reagents. This is the hardest part of this. So like I often do a little experiment with students where I take some salt and I have them pour it into a glass of water and stir. And you say, okay, where's the salt? Well, it's in the water. And I say, okay, take it out. And I'm like, what? Take it out? You know, once it's dissolved in there, you can't take it out. Well, that's basically what we're trying to do with direct air capture, is unmix the CO2 from an incredibly dilute, ppm level dilution of this stuff out in the atmosphere. This is estimated to cost about $600 a ton of CO2. There's other technologies, for example, putting certain mineral dissolution products into the ocean to increase the alkalinity of the ocean. This may change all sorts of things in the ocean, but it could allow the oceans to increase their ability, increase the solubility of CO2 in the oceans. There's still this problem with the oceans not being well mixed. You only have a few hundred meters of ocean that's actually in physical contact with the atmosphere, but that 100 meters could be made to be more CO2 hungry by changing its chemical composition. CO2 mineralization, kind of related. Basically, we take CO2 and concentrate it and then mix it into some sort of rock debris. There's a huge mine in Iceland that's doing this, where they're pumping concentrated CO2 liquids down into boreholes and allowing it to react with the basalt at depth. Of course, the whole world is not Iceland. They have a lot of renewable energy they can use to drive that machine. Otherwise, you have to mine the basalt and bring it here, or perhaps go to like Cyprus and bring back olivine and peridotite, and that works even better than basalt. But it's essentially a materials limited process. You'd have to mine an enormous amount of basalt to react 37 billion tons of CO2 per year. Soil carbon sequestration, again, this is a land use practice, changing the way that we manage forest soils, agricultural soils, no-till, low-till, changing nutrient cycling processes in agriculture. These sorts of things can certainly suck up some CO2, but none of them can reach the scale that we have been talking about with some of the first methods. The ultimate storage of this stuff involves finding a place that is suitable in the ground, injecting CO2 saturated brine down into saline formations in the porosity in the rock underneath cap rock, you have to have a very specific rock environment. It's rather rare, sort of like finding oil, right? In fact, it's pretty much the same places. So oil and gas industry is big into this because they get paid once to pull the oil and gas out, and they get paid again to put the CO2 back in. Other challenge, of course, is gathering the CO2 from wherever you're going to get it and getting it to those few places on Earth where you can store it in the rocks. So where can we put it? There's a range of these things. We can put it in seafloor basalt. We can put it in weathering of peridotite. We can put it on land. Ultimately, the amounts are pretty small. So on the x-axis here, which is logarithmic, you have the capacity to store CO2 per year. And remember, we're currently producing 37 of these gigatons per year. So that's like almost the very rightmost part of this graph. That's sort of the max that you could possibly put away. And then on the y-axis is the cost per ton, and that's also logarithmic. And you see that the sort of bulk of these methods is in the, let's say, $100 to $500 a ton. There are a few of these mineral reaction methods that could be an order of magnitude cheaper than that, but they are rather limited in terms of how much carbon you can store there. So let's say $100 a ton is sort of a middling number for this. I'm going to share with you the carbon arithmetic hat tip to Maury Wolfson. A gigaton of carbon reacts with oxygen to make 3.7 gigatons of CO2. That adds about a half a ppm to the CO2 in the air. So each gigaton of carbon turns into half of a ppm of CO2. 1 ppm of CO2, therefore, weighs 3.7 gigatons divided by 0.47. Let's just call that 8 billion tons. So each ppm of CO2 weighs 8 billion tons. And carbon dioxide reduction costs, let's be optimistic and call it $100 a ton, which I just showed you on the previous slide. So you do the math, you got 8 billion tons and it costs $100 a ton. That's $800 billion per ppm of CO2 that it's going to cost. And just to give you a ballpark of what that means, that's about equal to the US Department of Defense budget. So removing a ppm per year would cost the entire US defense budget. That's a shitload of money. That's just a scary number, especially if you want to drive it down 100 ppm, down to 350 ppm or something like that. So this is a very, very expensive proposal. Worse than that, it is thermodynamically unfavorable. Physics is against you. It is easy to oxidize condensed carbon in an oxygen atmosphere. This is easy peasy. It liberates a huge amount of energy. That's why we do it, right? It's cheap. It's exothermic. The coal is right there in a lump. You throw it in the fire, out comes all this energy. It's fantastic. We love doing this shit. We've been doing it for hundreds of years. On the other hand, it's super duper hard to capture dilute CO2 gas at parts per million levels, and extracting that carbon in an oxygen-rich atmosphere is really hard because you're trying to pry this carbon off of the oxygen with oxygen all around it. This is going to consume a huge amount of energy. It's not only expensive, it's very strongly endothermic. In fact, you use more energy capturing that carbon than you got by producing that producing the energy with the fossil fuel in the first place. So not only do you need vast amounts of money to do this, you need vast amounts of energy. How much energy? The US Department of Energy estimates that if you have enough breakthroughs, enough economies of scale, you can probably get direct air capture to reach an efficiency of something like 5 billion joules per ton of CO2. To give you a sense of that, the world's total energy production, not just electricity, but all energy, fossil, nuclear, hydro, everything put together, is about 6 times 10 to the 20 joules. So offsetting just the emissions that we have today would use 31% of global energy. That's a scary number. That means we have to divert 30% of the global energy supply to these fans that are being sold to us. Also, if you also wanted to remove CO2, not just offset the emissions, but remove CO2, a ppm per year would take 8% of the global energy system to suck down that CO2. So we are talking about not just a ginormous amount of money, trillions of dollars, but also an enormous expenditure of energy. And of course, where are you going to get the energy? You can't get it from burning fossil fuels. You're going to have ginormous amounts of solar and wind and nukes and hydro, geothermal. And of course, if you had all that solar and wind and nukes and geothermal, you would use them to keep the lights on, and you would rather not use it all to suck up the CO2 in the air. So that brings me back to this silly cartoon about mopping up. We're too busy mopping up the floor to turn off the faucet. If you come into your house and you realize that you left the faucet on and it's overflowed all day and it's coming down through the drywall and it's, you know, pouring out of your light sockets in the kitchen, probably the first thing to do is not to get a mop. Probably the first thing to do is turn off the stupid faucet. So do we really have to suck up CO2? Maybe we do. You know, if we don't get our act together and if we don't stop setting carbon on fire really, really soon, we may have to spend trillions and trillions of dollars and most of our energy trying to clean up the mess that we've already made. But that would really suck. Let's do as little carbon dioxide removal as we possibly can by going all out on faucet reduction as soon as possible so that we don't leave our kids with this horrible, expensive mess to clean up. Sure, it's technically possible to get a mop, but let's try to not make the mess any worse than it already is. All right, so that's my talk, and I will now be happy to take your questions.
Going to the first question, can 1 billion hectares of added forest help significantly absorb carbon? And you may have addressed that.
Well, so to be honest with you, I have a hard time in my head seeing 1 billion hectares. So I'm not sure I quite have that. Let me answer it this way. To offset 1/10 of our current fossil fuel emission, we would have to plant forests on land the size of India. So reducing our emissions by 10% would involve taking agriculture land the size of India out of food production and putting it into forest production and then never cutting it down. So I don't know if that's 1 billion hectares, probably not. I don't know how big 1 billion hectares is.
Yeah, it was like I did a quick on Google, and it said about 3.8 million square miles, I think, if I did that right.
So,
if it answered me right.
How big is India? If you could do all of India, that would be a 10% emissions reduction.
Okay.
So that's probably feasible, but you think food inflation is bad now. If you take an area the size of India out of food production, it's going to get expensive to eat. And that's only 10% of emissions. Then there's the other 90%.
Okay, here's a similar question regarding coastal ecosystems, adding to the non-ice coastline to increase like mangrove swamp, salt marshes, seagrasses, and so on.
Yeah, that's a good idea. That would fall under the land management, soil carbon sequestration bucket of solutions. Remember that you have to do it permanently, right? You have to stop doing whatever you're doing with that piece of land and start growing mangroves or start growing seagrasses. So pretty much yes, you can sequester carbon that way, and probably per hectare, arguably more than you could in dryland forest, but that's a lot of hectares. I mean, you really have to buy up all the coastal real estate in the world and convert it into those very high carbon landscapes, and it's expensive. What is a hectare in LA cost? I don't know.
Okay, adding a similar question, but I'm going to remove because you already spoke to part of it. And this is something that has come up in some previous presentations we've had recently at our conference, but about kind of restoring grasslands and I think more broadly the soil
Yeah.
carbon uptake.
So that's another good one. Now grasslands don't have as much carbon per hectare per acre as a forest, right? If you I mean, God forbid, if you dug up a hectare of all the soil in a grassland and weighed the carbon, there would be less of it. Not you know not 100 times less, but somewhat less than there would be in a hectare of forest. And healthy grassland will store more carbon than a farm. And then there's also a lot you can do with farms. You can manage agricultural soils to sequester carbon. You can change the way that you till or don't till, change the way that you feed the crops, change the way that you irrigate the crops in such a way that you try to stabilize the carbon in the soil. Another sort of version of this is biochar, that you take carbon and essentially drive off the volatiles to make it yucky to microbes so that the carbon doesn't decompose in the soil with exposure to bacteria. So there's a whole range of these. Typically, the limit is land, right? The limit is having enough land to store the carbon at a reasonable, kilograms per hectare.
Okay. Actually, we were going to have, I can't remember the name of the professor, but he's at CSU, and he was going to give a discussion on soil biology. And he had he had an emergency, had to cancel, but hopefully we're going to have that rescheduled for.
There's a bunch of people here that work on that, so you should talk to them.
Yeah, we'll have that hopefully rescheduled in the beginning of the year. So here's a question about the direct carbon capture. If strong bases are needed to absorb the CO2, specifically calcium hydroxide or calcium oxide, where does the strong base come from? Aren't most made by thermal decomposition of carbonates, which would produce CO2?
Yeah, well, that's a non-starter right there. You can't. So the commercial versions of this, like Climeworks, is the sort of leading company in that space. They are using an amine solution, which is it's like ammonia, but it's organic ammonia-like base. I think you're exactly right. Not so much CO2 as energy is required to process to regenerate the reagent. But my understanding is that no matter what you use for that kind of chemistry, the energy intensive step is to drive the CO2 out of the solution and capture it, and then regenerate the amine solution to recoat the beads. So they've been working on all sorts of different ways to do this with, geothermal heat or sunshine or whatever. And obviously, you'd have to pair these facilities with some kind of renewable energy, right? You'd want to see the big fan arrays next to giant solar panels or next to wind farms or next to nukes or something like that to be able to generate this massive amount of energy to be able to run the fans and regenerate the base. And it's going to use a tremendous amount of energy. I mean, I don't think they're getting it out of calcium carbonate. I think they're getting it in another way.
Okay. How would you store CO2 forever and be sure it wouldn't leak?
Yeah. Well, so nature has been storing carbon for hundreds of millions of years that hardly leaks, right? Think about oil and gas, right? Oil and gas is typically trapped in the porosity of porous rocks, sandstones, Actually, nowadays we get it out of shale, but I mean, it's in the microscopic spaces in the rocks, just like water is, and it is prevented from leaking by being underneath rocks that are impermeable. So I know this is, you all heard of that before. We can think of places where it leaks out, right? Like the La Brea tar pits, or the ocean off of Santa Barbara is full of tar balls and stuff like that that seep up out of the ocean floor. You think about like Judd Clampett, right? Up through the ground, come a bubble and crude. But on the whole, that stuff stays down there for millions of years. So that's kind of the idea, is to find brine reservoirs or depleted oil reservoirs and pump liquid CO2 into that porosity. And just like the oil and gas stayed under the rock for millions of years, the CO2 would be, hopefully stay down there. The Iceland solution is more aggressive than that. It's actually finding chemically reactive rocks, creating porosity by blasting or drilling or something, and then pumping the CO2 in there so that it reacts with these alkaline rocks to form calcium carbonate at depth. So then it's no longer liquid, it's not going to leak out, it's basically a mineral. So I think that's the answer. The question is whether you can find enough places to do that, right? I have a buddy, Steve Pacala, who I think he was joking, but I'll give you an idea of this. He said, if you took all of the fossil fuel CO2 in the United States and injected it equally everywhere in the United States, it would raise the ground surface by 1 centimeter per year. Well, gosh, that suggests we don't have room for it, right? So I think he was exaggerating, but remember, 1 gigaton is the Washington Mall, 10 times as high as the Washington Monument. We have 37 times that much stuff to get rid of. Holy moly, that's a lot. Every year, you got to find a hole in the ground that big. That's hard.
Okay, question on the BECCS. Is there a way to grow food like corn and take the waste biomass, the corn stalks, for satisfying that need?
Yes, and of course, in that case, doesn't have to be corn, right? It could be anything. Any sort of waste biomass. You can. So I guess let me see if I parse this question right. The reason why people like biomass energy crops for this solution is that they are getting energy out of them, right? The idea is that you actually extract the photosynthetic energy from, say, corn or soy, use that to keep the lights on, power vehicles, whatever, but you put the carbon back in the ground. If you did it with waste biomass, which could be grass clippings, it could be sawdust, it could be anything, then you could still sequester carbon, but you wouldn't get the energy out of it. So you'd have to then provide that energy in some other way. So I think the reason that BECCS is being considered is that some of the cost is offset by the production of energy.
Okay. James Lovelock said biochar was the only possible CDR solution. What are your thoughts on that?
I'm surprised that he said that. I mean, I listed about 8 solutions in this presentation, so I think there are these other possible solutions. I think biochar is intriguing, but again, we got to consider the volumes involved, right? So maybe if I say it differently, because nobody's relating to the Washington Mall. The CSU campus is about 1 kilometer wide by 1 kilometer long, and if you piled biochar a kilometer deep over the CSU campus, it would weigh much less than 1 gigaton, because the biochar is pretty light stuff compared to like water or something. Anyway, you have to put 37 times that much in the ground every year. Oh my God, that's an amazing amount of biochar. So before you can put it in the ground, you have to make it. Oh my God, that means you have to collect vastly more than that of vegetation. Let's say waste, biomass, sawdust, corn silage, whatever. Then you have to cook it with energy to make biochar out of it. Then you have to transport it to wherever you're going to put it. Then you have to put it in the ground. You have to do this year after year after year. I mean, yes, you could do this. I agree. I can't imagine why you would say that's the only way we could do this. There are these other ways too, but every one of these ways suffers from the Maury-Wolfson problem and the Scott-Benning problem, okay? The Maury-Wolfson problem is the US defense budget to reduce CO2 by 1 ppm. Oh my God, that's a lot of money. And the Scott-Benning problem is it's endothermic, right? You have to generate massive amounts of energy to be able to gather up the CO2, whether it's biochar or anything else, and stick it in the ground. Did I answer that?
I think so. Let's see. The IPCC has stated that CDR will be required. You seem to feel that this is incorrect, that we don't have to worry about it if we stop emitting.
That's what I said. What I said was, there's two things I'd like to push back on there. One, the IPCC doesn't say CDR is required. What they do is they model different ways to limit warming to 2 degrees Celsius. And most of the ways that they do that modeling includes quite a bit of CDR. So that's not quite the same thing as saying it's required. It's more like we can get there through a mix of emissions reductions and CDR. The other thing I push back on is I didn't say we can't do this or that we shouldn't do this. I said we might have to do this. In fact, I worry that we'll have to do a lot of it. And the trouble is it's super hard. It's way harder than emissions reductions, and it's way, way more expensive than emissions reductions. So the more we can front load the solutions on stopping the mess from getting worse than it already is, the less of this last resort CDR stuff that's way more expensive and way more difficult we will have to do. So I don't say we won't do this or we won't have to do this, or I certainly don't think that it doesn't matter. I do think it matters. And I think that the balance between emissions reduction and CDR is a no-brainer. On the emissions reduction is cheap and easy, the CDR is hard and expensive.
Okay, on to the next one. If we produce green hydrogen using, PV and electrolysis, true green hydrogen, which can give us a stored form of renewable energy, with that we can overcome the variability of renewable energy as a question. And
well, sure. So there are many ways to overcome the variability of renewable energy, and green hydrogen is one of those ways. It seems like a good part of the solution, especially for certain kinds of energy that is required to be very hot and very concentrated. So, for example, jet fuel or smelting ore or something like that, where you need a lot of energy, very concentrated in a small space that can be stored. But there's lots of other ways to do that too. For example, transmission is a tremendous improvement on the variability of renewable energy. Pretty much goes away if you have enough transmission. It's always sunny somewhere, and it's always windy somewhere. So if there's enough connection across space, the variability goes down dramatically. Then, of course, there's all kinds of energy storage, of which green hydrogen is one, right? Green hydrogen is basically just a subset of the category energy storage. Heat in the ground, batteries, pumping water uphill, pressurizing air, running train cars full of gravel up a slope. All those things are sort of green hydrogen equivalents in terms of managing variability in the energy system. So there's a lot of solutions, and I think CDR belongs in that list too, right? CDR is a bunch of different tools. They happen to be very, very expensive and very, very energy hungry. So to the extent that we can mitigate these problems without going straight to the most expensive solution, I think we should.
Okay, moving on here. And does hydroponic farming help in lowering carbon per acre?
So this is not my specialty, but I'm gonna say that it depends. So if the hydroponic farming is replacing some sort of very carbon intensive agriculture, like say, feedlots, then yeah, but of course you don't grow beef hydroponically. So it depends what it's replacing, right? If you're growing a crop in water with nutrients in the water that avoids having to till the soil and release a bunch of stored soil carbon, that's a good thing. I don't know that you could really replace all of agriculture with hydroponics, though.
Okay. A question for Maury. Have we yet turned the corner regarding the extent of naive public enthusiasm for carbon dioxide removal? How much more education is needed for researchers and innovators to ramp down their pursuit of these solutions?
Well, I don't know about public. Yeah, probably not. Public naivety seems pretty deep. So, of course, there are hucksters, in the world, and it isn't just carbon dioxide removal hucksters. Think of used car salesmen, right? I mean, there are people that'll sell you just about anything, and unfortunately, that's where we are with a lot of these technologies. We are in a stage where people are trying to get venture capital, and they're trying to get hype around their companies, and they're trying to sort of sell the public on this being a quick and easy way to avoid having to cut emissions. But it's actually, I would argue, just the opposite. It's much, much cheaper and easier to cut emissions than it is to remove CO2 from the air. And so it is in our financial best interest to put as little CO2 in the air as we possibly can so that we don't have to pay through the nose to take it back out.
Okay, next question. It almost was like on cue. If we hold off on worrying about CDR and focus on emission only, historically we have not been effective at stopping emitting. Yes, this must occur, and we can't afford to wait on these other methods that will require and we can't afford to wait, I'm sorry, on other methods that will require R&D, scaling, et cetera. Basically, shouldn't we just be all hands on deck? I just summarized that last sentence there.
Yeah, I think we should be all hands on deck. I mean, I think, I'm not sure that a lot of people are trying to frame this as either or. I think we have to have a crash program to produce energy that does not involve combustion. And it has to scale up really, really fast. And the faster and more effectively that non-combustion energy scales up, the cheaper it's going to be. I know it doesn't sound possible, but you know, at $600 a ton for direct air capture, you could buy a boatload of solar panels and batteries for that kind of money. So I don't think we want to just put it on the shelf and not do anything. I think there's a lot of research going on. In fact, the U.S. National Academy of Science just came out with a big voluminous report that details all of these different carbon dioxide capture methodologies and also other kinds of geoengineering, things like solar radiation management, albedo management, stuff like that. And far from saying that these are scary, let's not do them, they say this is going to take a lot of R&D. This is going to take decades of thinking about this and trying to get our heads around how to do it well and safely. At the same time, we hope to not have to do very much of it because it's going to be punitively expensive. It's really, really hard. I just can't say that enough times because people aren't getting it. That you think, well, this will be easy. We'll just suck the CO2 out of the air. No, it's way, way harder than not putting it up in the first place.
Okay, here's a little less controversial question. How can building materials be part of the carbon sink equation?
Yeah, that's a great one. So building, depending on how you slice it, buildings, life cycle of buildings is something close to half of all energy use in the developed world. So from mining the ore to smelting the steel to transporting the materials to erecting the buildings to operating the buildings to then tearing them down when you're done. So I think that's a soup to nuts life cycle question, and it's not just building materials. It's how we design buildings and how we site them and how we occupy them and how we operate them. But yes, it's materials too. I know that there are some very interesting things going on with engineering of wooden skyscrapers. Oh my God, imagine that. I'm not sure I would want to live in one, but you could imagine carbon being stored in a sense in buildings instead of used to make the steel that is then stored in the buildings. But I think that's actually a huge growth area, and there's a really wonderful project called Architecture 2030 that now involves something like 70% of all commercial architects firms in the world. Architecture 2030, they are committed to building nothing but net zero carbon buildings by 2030. And we're talking about like every major commercial architect on earth, right? So Singapore or Beijing or Shanghai or whatever. And not only do they pledge to do this, but they develop architecture software and kits and seminar series and courses about net zero carbon building design and operation. I think that's a very exciting area.
Okay, so we're addicted to burning carbon. So how do we break this cycle quickly? It's doable, but like telling the addict to quit cold turkey, people aren't that motivated to change their lifestyle choices.
Right, and we can't actually quit cold turkey. I mean, if we're really aggressive about it, we can cut emissions by half in a decade. That's not really cold turkey. That's like the heroin addict, only doing half the hits for 10 years. So how do we do this? There's just a huge range of things that all have to happen, right? We have to use energy more efficiently. We have to make electricity without combustion, and then we have to electrify everything. And by everything, I mean, transportation, heating and air conditioning, cooking, everything manufacturing has to be electrified using clean energy. The electrical grid has to be made much more resilient to variability so that we can move the non-carbon energy from where we have it to where we need it at a moment's notice. We have to build in some storage. Storage is more expensive than transmission. So just like the CDR versus emissions reduction, you want to do as much inexpensive transmission as you can to avoid the very expensive storage. And then, of course, there's all these sort of lifestyle changes we can do, right? There's the you know, the stuff your mom told you, like turn off the water when you're brushing your teeth, wear a sweater in the winter, don't run the air conditioning down to 65 in the summer, and all that kind of stuff. So all of these things taken together, we're actually making some significant progress. I mean, in the United States, emissions are down by about a quarter. That's pretty remarkable, just since the like Lehman Brothers collapse, the Great Recession. In China, emissions have stopped growing. They're basically flat. I mean, that's not down, but that's way better than it was 10 years ago. I think something like I don't know the statistics here, but the electric transportation much faster in China than it is here. Tremendous progress on electrifying the vehicle fleet in China, and that's actually where most of the cars are. So I think there's a lot going on. I think yes, we have a huge problem here. Unfortunately, cold turkey probably isn't going to happen, and we're going to have to work as fast as we can, because if we don't, we're going to be stuck with the bill for CDR, which is punishingly expensive. So yeah, we got to get on all fronts. We got to be moving forward.
Okay, here's a good one. I was kind of waiting for this to pop up. It's been postulated that ending animal agriculture could free up enormous amounts of land that could be reconverted back to forest, and you know, and basically just avoiding having to feed the animals, to paraphrase the last part of that question.
Well, that's right, and that's also not an either or. I mean, every bit of animal agriculture that we reduce is going to save carbon and energy. We are just profligate with the way we emit carbon from agriculture. But even taken all together, even with the fossil fuel part of agriculture, it's no more than about a quarter of all greenhouse gas emissions. And so there's no getting around the other 3/4, which is the energy sectors. But yeah, we should all eat lower on the food chain. We need to manage our agricultural land better. I don't think you could actually replace all grazing land with forest, because it wasn't forest to begin with, right? Think about you know, eastern Colorado, where we graze a lot of cattle. Stopping the cattle would not make a thick green forest out there. There's just not enough rain to make a forest. So that when I say there's only so much land where you can grow trees, I'm thinking eastern Colorado is not one of those places, right? I've been out there. It's awful dry.
Okay. Question on specific. Can you provide your perspective on the carbon capture technology being commercialized by Heirloom that uses carbon mineralization? I don't know if you're familiar with that.
I don't know that I know Heirloom, but I do know about carbon mineralization. So I just actually, a buddy of mine has one of these companies and gave a presentation last week at a meeting, and I was so what I don't know about Heirloom, but this other technology involves alkaline rocks. So when you think of rocks, think of like the white rocks and the black rocks, right? The white rocks are the granites and the black rocks are the basalts. The basalt is the entire floor of the ocean is underlain by basalt. And then there's a beyond basalt, a super, we call it ultramafic, a very alkaline bedrock, which is comes from the mantle, and you have to mine it. You have to go to places like Cyprus to mine it, or Newfoundland. Anyway, this stuff is imported by a company, and ground up into a very fine powder, like talcum powder, and then it is made into a slurry, and you run a tractor through your field, laying down this slurry of ultramafic powdered peridotite mineral, and it gets into the agricultural soils, and because the ag soils are quite productive, full of carbon and roots and dead plant material, there's lots and lots of CO2, maybe 10 times atmospheric CO2 in the pore space of the soil, and that highly acidic soil water reacts very aggressively with this powdered alkaline mineral, and that actually turns into dissolved stuff that flows down in the streams and becomes ocean alkalinization. So that's actually like an acceleration of the natural process of chemical weathering, and that's how the Earth itself has balanced the carbon cycle over 1 billion years. I'm not sure there's enough peridotite on the surface of the Earth to make that commercially work, even though my dear friend is selling this to investors. So I don't know about heirloom, but it's not a crazy idea. It's a reasonable extension of a natural carbon solution. It's expensive. I think the reason why people are getting away with doing this and doing it for a profit is because there are customers, right? I mean, even if it's $600 a ton, if somebody is willing to pay that $600 a ton, and you're the guy with the mine of peridotite, I guess that works for them.
Okay, well, there's a couple more just statements in support of the discussion. So just some good thank yous, and so if there's no other questions, I definitely want to thank Scott again for another presentation, a great presentation, and Scott does have a couple of other recordings that kind of go into deeper dives on this. So Scott, if you get those over to me, I will be able to send it to all the registrants. So kind of this is the executive overview, and then the deeper dives should you want them. So
okay, well, thanks a lot. It was a lot of fun, and I hope to catch up with you soon.
All right, okay. Thanks again. Thanks, Scott. Have a great evening.
You too. Bye-bye.